Salt, diamond, copper, water, utterly different materials, yet all built from atoms doing one thing, getting to a full outer shell. The way they reach that full shell is the bond, and the bond decides everything. Whether a substance melts at 800 degrees or boils away as a gas comes down to how its atoms are stuck together. This unit is the rulebook for sticking atoms together. We meet the three strong bonds, see what happens when sharing is unequal, then the weaker forces acting between whole molecules, and finish by predicting the actual shape a molecule takes in space. Get bonding, and the rest of chemistry has a backbone. First stop, the two classic bonds. In ionic bonding, a metal hands electrons to a nonmetal. Sodium gives one away, chlorine takes it, and the two opposite charges lock together by electrostatic attraction. The giveaway sign is a metal plus a nonmetal, producing a brittle, high-melting solid like common salt. In covalent bonding, neither atom will give an electron up, so they share a pair instead, and the shared pair belongs to both nuclei at once. Two nonmetals do this, like the two hydrogens in hydrogen gas. One special case, a dative bond, where both shared electrons come from the same atom, as in the ammonium ion. Next, metals. Picture a lattice of positive metal ions sitting in a sea of delocalized electrons that have broken free and drift through the whole structure. That shared sea is the metallic bond, and it explains metals at a glance. The loose electrons carry current and heat, and the layers slide without shattering, so metals conduct and bend rather than snap. So three strong bonds, one common goal, a full outer shell, reached three different ways: give, share, or pool. And the strength of these bonds is exactly why ionic salts and metals stay solid at room temperature, while many covalent molecules drift off as gases. Strong bonding, high melting point, it is that direct. Now a subtlety. In a shared pair, one atom often pulls harder than the other. That pulling power is electronegativity. When the two atoms differ, the shared electrons sit closer to the greedier one, giving it a slight negative charge and leaving its partner slightly positive. The bond is now polar, covalent, but lopsided. Why care? Because these tiny charges are the hooks that hold molecules to their neighbors. A bond can be polar, yet if the molecule is symmetrical, the pulls cancel, and the whole thing is nonpolar overall. Carbon dioxide is the classic trap. Always check the molecule, not just the bond. Polarity sets up everything that follows. Here's the idea students most often miss. When a simple molecular substance melts or boils, you are not breaking the strong covalent bonds inside the molecules, you are only pulling whole molecules apart from each other. Those weaker pulls between molecules are the intermolecular forces, and they set the boiling point. The weakest forces, van der Waals, exist between all molecules and grow with size. But the superstar is the hydrogen bond, an unusually strong attraction when hydrogen is bonded to nitrogen, oxygen, or fluorine. It is why water boils so absurdly high for its tiny size, why ice floats, and why life chemistry works at all. Last stop, shape. One rule does the work: electron pairs around a central atom repel each other and spread out as far apart as possible. Count the pairs and the geometry follows. 4 bonding pairs push to a tetrahedron at 109 degrees, 3 flatten to trigonal planar at 120, 2 go straight, a linear 180. The twist that catches everyone: lone pairs repel even harder than bonding pairs, so they squeeze the angles down. Water has 2 lone pairs, which bend it to about 104.5 degrees, not the neat tetrahedral angle you might expect. Count all the pairs, respect the lone ones, and you can predict any simple shape. Here's bonding on one page. On the left, the 3 strong bonds: ionic gives, covalent shares, metallic pools, plus polarity when sharing turns unfair. On the right, the forces between molecules, weakest to strongest, and the one repulsion rule that predicts every shape. Your drill: name the bond from the elements involved. Decide if the molecule is polar by checking its symmetry, then count electron pairs to get the shape. Bond energies, the numbers that quantify all this, feed straight into the energetics unit next. Lock in this page, and you can read why any material behaves as it does.